Okay, this time I'm going to get into using equations available on the machine to do more enhanced complex shapes. The video is showing the machine creating a face sloping downwards in the y direction. It's using the slotting command to pick down to the depth of that slope, and after it's reached the correct depth it resets the slotting command and steps over by a certain amount to create the next slot. While we're watching that, let's go into the maths of what this machine is capable of. So if we were to consider that the drill or cutter has infinitesimal diameter and I was pick drilling, the point on the XY plane that you make is actually got no dimensions. If I go the next step and decide to create a slot with this infinitesimal cutter, I would create a one-dimensional line. And finally, if I was to create a pocket with the pocketing can cycle, I would be doing the same thing in both x and y directions and do an area. In every case, the depth is set constant, and that's why they call this machine basically doing 2.5 dimensional machining. The slotting command is actually cutting back and forth in the x direction, and I'm using it because if I didn't, the depth of the plunge that it would make by just following down that slope would mean I'd start machining or trying to machine with the actual shank of the cutter. So I select a suitable pecking depth on the slot that I'm not taking too big a bite with the cutter on each pass. You'll have noticed that there are scallop lines from the cutter visible on the new face. The desired slope line actually touches all those scallops tangentially, so afterwards I can take them apart and linish it, and when the scallops disappear I'll be on the desired slope line. Or of course I could actually reduce the step over considerably and end up with the same effect. What I've also done is overscanned the slot and the Y movement to beyond the width of the machining blank, just so you can see that it stands alone as a slope. So now we'll get into the trigonometry of the program. This is a section view of the problem, looking more or less in the direction of the camera in the previous parts of the video. This line here is the datum height plane, XY, of the blank, the machining blank. This is the slope line that we want to cut along. So we can adjust this here to adjust that slope. Here is the maximum travel I want to do in the Y direction. And here is the actual point where the milling cutter is going to be cutting those scallops. These things here are, well, this is obviously the same angle, it changes with this angle. And here are the actual trigonometric equations associated with the particular dimension. And currently it's forced by the geometry of this to be 3.88 millimeters to where this contact point is. You'll notice also all of them have this Q number in front of them. And Q Q is used by the Heidenhain for variables, and they'll come up again in the equations that the Heidenhain will use to calculate these itself rather than have them on the sketch. But you'll see they all have a Q number. Heidenhain allows you to have variables, they call them Q, and a number from 1 to 99. So these are of my choosing, Q2, Q5, etc. I've chosen that number. I'm going to change this cutter radius here so it's a little bit easier to see what's going on. Okay, so I've made the cutter radius, or cutter diameter, extremely large, and you can now see that there's a little bit here, this bit here. This is where the cutter will be for it to be cutting at this point here. And this little distance is caused by the cutter radius. So it's a calculation using this triangle here and subtracting it from the main radius. The other main component that we're looking for is the length of this line here. And you can see that that's to do with this, the sine of this angle and so on. So there's two separate components to add up to this number over here, which is the final equation of what depth I should take the cutter down to in the slotting routine to cut over here. And instead of the actual cutter Y position will be along this line here, this distance here, the current Y, but in fact it's going to be cutting at this point here. So I have to take away or calculate using this compensation here to get from this point to here for the cutter to be in the right position to cut along the line. Okay, let's get into the actual program itself. I'm going to skip through all this stuff at the top. It's not particularly new stuff. And we'll get straight down here into the actual equations to make this program run. So the first thing I'm going to note is these P numbers all over the place, all the way through. They're parameter numbers. And the TNC 155 uses them all over the place in the same manner in the equations here and in canned cycles. And they're kind of odd. They're kind of redundant. You could simply replace them with a comma to separate all the variables. But they insist on putting P01, P02, P03 and on right through up to, in one of the cycles, you can get up to P012. So all they're really saying is that this number to the right here, in this case plus 0.5, is labelled P01. And this variable here, Q108, is labelled P02. And you can see here the explanation for what they actually are. It turns out that they store, the Heidenhain TNC 155 stores the cutter radius in a memory slot called Q108, a variable. And that's handy because I'm going to use that elsewhere. Okay, now we've covered them. Here you can see we go Q1, Q2, Q3, Q4 and so on, building up Q numbers. Each one is a variable of my choosing, and you can see that Q2 happens to be the length of the slope in the y direction, actually in the minus y direction, I missed that before, and so on. Slope in the x direction, the width of the slope, sorry, 45 millimeters in this case, and so on. You can shift the slope starting point if you want. Here's the angle of the slope down from horizontal, 15 degrees. This only has one parameter because it's just an angle, and it's stored in a variable called Q6, and so on. Okay, the next thing is these D numbers. So you can see we start with a line number, and immediately we call this D number. And if we look up here, we'll see it means multiplication. Now, for multiplication, you need two numbers. So if you look, it's going to take Q1, it's going to take P01 and multiply it by Q108, and it's going to put the number in the variable space Q1, and so on. You'll see that this has got to be one line or block of code, and all it can do is that one operation. It can't do that whole equation that we've seen in the previous video, part of the video. So you have to build up the equations one operation at a time. So we get down here and we can see that we've found the cosine, and then I have to subtract 1 from it. So here what we're going to do is take this first parameter, this first number, 1, and we're going to subtract Q10 from it. And Q10 here is cosine of the angle. So 1 minus cosine of the slope angle. When it's done that calculation, it's going to stick it in Q11, variable 11, and so on down. Slowly we build up and we build up as we go down, until finally we get down, right down here, to the final answer, Q18, the Z depth of the cutter. So you can see this way of doing equations, one binary operation at a time, is very lengthy, prone to typographical errors and so on. So these are the ones that are all fixed for the whole of the machining cycle. When we get to here, I preposition the thing, the cutter, and then I have to do a funny step over, because otherwise the calculation will get me above the datum surface, and you get odd, the numbers go wrong, get the wrong sign, and the slotting equation won't work properly. So that gets me on to the beginning of the slope. And then we go down here and we start doing an iteration that does the calculation necessary for the Y position, the calculation for the Z depth, and then it calls this slotting thing, and you can see here it's taking all these other variables we've done and put it in the slotting call. So you can see Q18 there and so on. Some of them aren't just numbers, but most of them are to do with cutter traverse speeds, cutter in-feed speeds, and so on and so forth. So finally we're using all these variables we've got to figure out what the slot parameters should look like. When it's finished doing the slot, it increments the Y position by the step over amount that the program's set for, and then it drops out of the subroutine, and here it does a check to see that it hasn't gone more than the maximum Y distance. If it has, it simply runs through and stops. Of course, the way this is written, you can get in here and change most of these variables to give you different slopes, different lengths, different widths of slot, and so on. And another point that's worth noting and passing, you'll see here that it takes the cutter radius, this Q108 variable, and it multiplies it, DO3, by 0.5, and it puts it in Q1. And it uses that for the step over. But down here, if you look at the canned cycle for the slot, It's also using Q1 for the peck depth. So that's just a bit of a cheat to make a decent size cut and depth change all in one step. Anyway, I think that's about all there is to talk about this. It's covered most of the foibles of it. It shows you that how you can only actually do one little part of each of those equations is solving one block at a time through a whole sequence. And a lot of these equations need some of these guys before, so it builds and builds and builds and builds all the way down through the program just to get that one, really just to get this one equation at the end, which you saw on the diagram, which is the overall slot depth. And just one last passing thing before I go. I'm just showing the screen here, and I'm stepping through the slotting cycle. You can see it's taking several lines on the screen. And as you step through, you can see it giving you the prompts that you get when you're doing ISO G-codes. Okay, I hope you haven't fallen asleep by now, and thanks for watching.